Okay, so before we consider this solution in detail, I just want to remind you about the idea of momentum conservation in any sort of collision. The idea of when two objects collide, there's momentum transferred from one object to the other one. If the momentum of this object goes up, then the momentum of this object goes down, such that the total momentum is conserved. And remember that momentum transfer involves a force acting over time. Okay, so if we have any two objects, and suppose we're talking about contact forces. So remember that you can think of matter. A simple model of matter is, point particles connected by little springs. So they're all like springy a little bit. So now we have these two objects coming together, and when they touch, they're exerting forces on each other. And those forces, Newton's third law, action and reaction pairs of forces. So those forces will compress those springs. Those objects will compress a little bit. Okay, and then like compressed springs, they will uncompress again, and then they will fly apart. So it's like two springs colliding like this. Okay, so we can imagine it sort of like this. We're going to imagine that we've got one object which is moving to the right slowly, and another object which is moving to the right fast. So this one's going to catch up with the other one. Okay, and so the collision is going to look like this. So they're going to come like this, and then they're going to touch, and then the objects will compress a little bit, and then they will uncompress, and then they will fly off again. And we're going to represent that compression of objects with springs. Okay, so we're going to say that we've got an object of mass little m, which has a spring attached on the right-hand side like this. And we have an object of mass big M, which also has a spring attached this to the left-hand side. And so when they come together, then these springs are initially relaxed. When they come together, they touch, and those springs start to compress, and then they compress maximally, and then they uncompress again. Okay, so we can imagine, for instance, that big M is moving slowly to the right, and little m is moving fast to the right. And so they will eventually catch up. Little m will eventually catch up with big M. The spring will compress maximally and then uncompress again. Now the thing about a spring, remember, is if I take a spring in my hand and compress it like this, well then whatever force I'm applying to the right side of the spring is of equal magnitude to the force I'm applying to the left, which is the same thing as saying that that compressed spring is exerting a force on my right hand to the right and a force on my left hand to the left of exactly equal magnitude. That's the important thing. Okay, so at some instant of time during this collision, we've got these springs are, say, partially compressed, and the left end of this compressed spring is, we're imagining these are massless springs, okay? So this left end of the spring is exerting a force on little m. So there's a force on little m due to big M at that instant of time, which is to the left. But whatever that force is, there's an a force of exactly equal magnitude opposite direction that the right end of the spring exerts on big M that way. So that's force on big M due to little m at that instant of time. Okay, so that's great. Now remember, this is the crucial thing, is that momentum is transferred by a force acting over time. Okay, so this force is going to act on big M over time and transfer momentum to big M. This force is going to act on little m over time and transfer momentum to little m. The key is that these two forces are equal in magnitude, okay, and they're acting over the same amount of time. And so that force acting over time transfers the same magnitude of momentum, but they're in opposite directions. Okay, so if this one gains a momentum, say, +5, then this one will lose a momentum of 5. So this will go up by 5, this will go down by 5, and so the total momentum in that system remains the same, even though there's momentum being transferred from one system. All that's happening is momentum is being transferred from one system to the other by the action of forces acting over time during the collision. Okay, so we can say, like work done is force acting over distance, is energy transferred. We had, instead of work done, force over distance, we have, or force dot displacement, we have impulse, which is force acting over time. So the impulse imparted, let's say, to big M here, well, what is that? Well, it's the force F big M little m acting over time. So we take the force big M, F big M little m, at any instant of time during the process of the collision. We multiply by dt and we integrate. This is a force acting over time. And what that's going to do, this force acting over time is going to transfer momentum to big M, to the big M system. And we called that delta big P. Okay, so that's equal to big M times big V prime minus big V. big M times the change in velocity of big M. Okay? But now we can ask exactly the same question. We can do exactly the same analysis to little m. So we can ask, well, what is the impulse imparted to little m? Well, the impulse imparted to little m, well, it's going to be the force acting on little m. It's the force on little m due to big M at some instant of time during the collision, and then we integrate that over time. And so the force F little m, big M, acting on little m over time, imparts impulse to little m and transfers momentum to little m. Okay, and so there will be a change in the momentum of little m, which we call delta little p, which is this thing, little m times final minus initial little v. Okay, and then the crucial thing to notice here is that F little m big M is the negative of F big M little m. Okay, and so this is exactly the same as this except with a minus sign. Okay, so this integral is the negative of Im. So the impulse, if there's an impulse of say 5 imparted to big M, then there will be an impulse of negative 5 imparted to little m. Okay, and this negative I big M is negative delta P. Okay, so the momentum transferred, whatever momentum is transferred to, suppose it's to the right here, whatever momentum is transferred to big M, there's an equal and opposite momentum transferred to little m. If this momentum increases, this momentum decreases by exactly the same amount, so that the total momentum in the system is conserved. Now this is completely general, and this is always true here, regardless of the nature of these springs. Okay, so if the springs are not ideal springs, like it's like two balls of putty coming together, and the springs get compressed and stay compressed, right? Then we'll still have conservation of energy, but then some of the original kinetic energy will go into other forms of energy, like thermal energy and so on and so forth. The idea of perfectly elastic is that the elastic nature of all bodies is in this case perfect. Okay, and so these masses come in like this. There's some kinetic energy in the system. Okay, and then these two ideal springs compress. There is now less kinetic energy in the system, and that less kinetic energy, there's been some kinetic energy in the system which has gone into spring potential energy. Okay, but then those springs uncompress, and then they re-release that potential energy they had stored back into kinetic energy. So whatever kinetic energy those two objects had to begin with, it comes back to them, and we have the same kinetic energy for those two objects finally. Individually, the kinetic energy might change. This one is at rest to begin with, and this one's in motion, and then they collide, and maybe this one comes to rest, and now this one has all of the original kinetic energy. But the total, so the kinetic energy individually of little m and individually of big M can change, but the total kinetic energy remains the same. Okay, so just wanted to sort of remind you about that. Okay, so now let's go back to this problem here. So we've said delta E other is equal to 0. And so if we look at this equation number 2, that disappears. And so then this thing is equal to 0. Well, delta P, if that's not 0, then we have little v average minus big V average is equal to 0, or same thing as little v average is equal to big V average. Okay? Now remember, V average is initial plus final divided by 2. Excuse me. And so little v average is little v prime plus little v divided by 2. So little v prime plus little v divided by 2. That's equal to big V average, which is big V prime plus big V divided by 2. So getting rid of the divided by 2, that's the same on both sides. We get this equation. Okay? And so when we use equation number 3, the assumption that none of the original kinetic energy is converted into other forms of energy like thermal and so on and so forth, then that drops out, and equation 2 becomes a new equation, which is this thing. We'll call that equation 2 prime. Okay? So now, indeed, we do have two equations in two unknowns. The two unknowns are little v and big V prime. They appear in this equation, equation 1, and they appear in this equation, equation number 2 prime. Two equations in two unknowns. Okay? So now I'm going to assume that all of you know how to solve two equations in two unknowns. You can do that by substitution. Substituting, say, little v into this equation and playing around with the equations and so on, and eventually solving for the two unknowns, little v and big V prime, in terms of the initial velocities that we were given, little v and big V. Okay, so you can solve by substitution, or if you know a little bit about matrices, this is a very simple 2x2 matrix. You can write these two equations as a single, very simple 2x2 matrix equation, and then you can solve it doing that, invert the matrix and so on. So if you know about matrices, I encourage you to solve it that way. If you don't, just solve it by substitution, or however you want to do that. So anyways, I'm assuming you know how to solve two equations and two unknowns, so I'm not going to bore you with the details. I'll just write down the solution. Okay? And the solution is this. The final velocity of little m, so that's little v prime, turns out to be little m minus big M over big M plus little m times little v plus 2 times big M divided by big M plus little m times big V. So that's, let me see, am I going to have enough room? Yeah, let's write it over here. Okay, and then we can, so that's one of the unknowns, the final velocity of little m. The final velocity of big M is big V prime, and big V prime has a very similar form. It looks like big M minus little m divided by, actually, you know what? I'm going to write it this way. I'm going to swap this around. Big M plus little m. I'm going to write this as little m plus big M. And you'll see why in a second. So the big V prime is this times big V, okay, plus twice little m over big M plus little m times little v. Okay? So when we solve two equations for two unknowns there, this is the solution that we get. Okay? Let me just say, before we even look at this solution, the idea in physics is not to memorize something like this. If your inclination is to memorize this, don't. So we want to go from, Bloom's taxonomy, memorization is down here. We want to go up to the next level, which is understanding. So never memorize something like this. What you should be able to do is, starting, you should be able to derive these two equations, make this assumption, and then get that, and then solve these two equations and two unknowns to get that. So that, excuse me, that's, illustrating some understanding. And so never memorize an equation like this. Well, let me point something out about this equation. So you can see that you can double check whether you've made an obvious mistake in this equation, because you'll notice that the solution for the final velocity of little m is basically exactly the same as the solution for the final velocity of big M. Except the only thing that's different is you have interchanged the masses, little m and big M. Okay, so if you take this solution for the final velocity of little m and replace the masses, you get little m minus big M minus little m, and this denominator is the same, and this 2 big M becomes 2 little m, and this denominator becomes that denominator. Okay? And then you interchange, because you're interchanging the two masses, little m and big M, you also have to interchange the initial velocities, little v with big V. So that little v becomes a big V, and this big V becomes a little v. Okay? So that's an important thing. You need to start thinking in terms of like symmetries like that. Just look at the equations and look at sort of patterns and see that kind of stuff. So anyway, so that's a quick just double check that I didn't copy from my notes down wrong here. Okay, so now what we're going to do is we're going to look at these equations and see what they mean, because they're very interesting. Okay, so there's two types of terms here. This kind of term with the difference of masses divided by the sum, and this kind of term, which is like twice a mass divided by the sum. Two different types of terms, and they and we're going to look at those two terms individually. And the way that we look at those things is we're going to imagine a situation where big V is equal to 0. In other words, the initial velocity of big M is 0. In other words, big M is initially at rest, but little m is moving towards big M. Okay, so remember that if you have any kind of collision, so suppose you've got, I don't know, you've got some object like this moving to the right, and you've got some object like this moving to the left like this, and they're coming together, you can always move to a new frame of reference that is moving exactly as fast, you can always run to catch up with this mass, so that this mass appears to you to be at rest. And this mass appears to you to be moving faster toward you. So you can always change your frame of reference so that this guy is at rest and this guy is moving a little faster. And so you can always replace any general initial velocity, initial pair of velocities, one-dimensional collision with a collision in which one of the objects is at rest and the other object is moving toward it, toward the first object. Okay, so we're going to consider, without any loss of generality really, we can sort of unravel the meaning of these equations by considering this special case, which is not really a special case. So we're going to imagine that big M here is initially at rest. So the initial velocity of big M, which is big V, is initially 0. And we've got this little m coming in with some velocity little v. And so now it totally depends upon the ratio of masses and so on. For example, if big M is huge compared to little m, then basically little m is going to bounce off of big M. If little m is huge compared to big M, then little m is just going to fly through like this. And so the final velocity of little m is going to be to the right, and so on and so forth. Okay, so there's all kinds of different situations that arise. So let's look at those situations. So remember, this is actually a completely general analysis of elastic collisions in one dimension, even though we're assuming that one of the masses starts out at rest. The advantage of doing that is we don't have both terms in these equations. So if big V is equal to 0, that term drops out from this equation. If big V is equal to 0, that term drops out of that equation. And then we can separate these two types of terms, one of them having a difference of masses in the numerator, and one having twice the mass, 2m, in the numerator. Now we can look at those two terms individually and see what they're saying, because it's kind of interesting. Okay, so let's see. Always an issue of space. Okay, so let's look at little v prime. So the final velocity of little m. Okay, am I going to have enough room here if I do it here? Okay, so this is v prime. Okay, so when the initial velocity of big M is 0, big V is 0, that term drops out, and we just have this. So it's little m minus big M divided by little m plus big M times little v, the initial velocity of little m. Okay, so we're trying to figure out what's the final velocity of little m. Does it bounce back, or does it continue forward, or does it come to rest? That kind of thing. Okay, so let's look at that. You can see that there's a difference in the numerator. So if little m is bigger than big M, then we're talking about v prime is positive, so it goes off to the right. If we reverse that situation, then v prime is negative, and it goes off to the left. So let's look at those cases separately here. Okay, so this is equal to, and there's a bunch of different cases here. Okay, so there's the case that this is positive. Okay, and this is going to happen if little m is bigger than big M. So this happens if little m is bigger than big M. So on this side, we're dealing with a situation that looks like this. Little m is big compared to big M. So big M starts off at rest, and little m is moving toward it like this. And this is going to be equal to 0, and this is going to be less than 0. So this is less than 0 if, how do I want to write this? Big M is bigger than little m. So if big M is bigger than little m, okay, then this final velocity will be negative. We're assuming, of course, little v is positive to the right. Okay, so we got that. So when big M is bigger than little m, that means this guy is big and this guy is small. So this guy, big guy, starts at rest, and there's a small guy coming in like that. Okay, so that's below here, that's above here. And and of course it's equal to 0 when little m is equal to big M. Now this example you are all familiar with, almost all of you should be familiar with this. So if you've ever played billiards, like pool, then if you have the white ball and the colored balls are basically exactly the same mass. And so the final velocity of, and we're going to have a head-on collision like this. So if you take a white ball and you hit a colored ball that's initially at rest, let me actually turn this way to do it. Okay, so you've got this colored ball at rest here, and you've got a white ball coming in of exactly the same mass. Then what happens is that white ball strikes the colored ball and comes to rest, dunk, and the colored ball takes off with exactly the same kinetic energy and momentum that the cue ball, the white ball, originally had. So there was exactly a transfer of the momentum. All of the momentum of little m went into big M. All of the kinetic energy of little m went into big M. So little m came to rest, and then big M started at rest, little m came to rest, and big M took on all of the momentum and kinetic energy of little m. So this is like for billiard balls. So in this case, we have, how should we say this? We have all. So all the momentum that was originally in little m and all of the kinetic energy that was originally in little m gets transferred to big M. Okay? Okay, so now in this case, let's look at this case over here. Okay, so if little m is big, okay, and big M is small, then what we have is that the final velocity of little m here is positive. It goes to the right, which makes sense. This guy's at rest. This guy is this big heavy thing. It comes like this, boom, and it hardly feels the presence of this guy. It just sort of plows through. Okay, and so the final velocity of little m is positive to the right. Okay, and then we can take the extreme case of this mass becoming like a tiny grain of sand and this being a big heavy thing. So when that happens, that means that big M, the mass of this guy, is tiny compared to little m. So in the denominator, little m goes to 0 compared to big M. So we can ignore big M here, and we can ignore big M in the numerator. And this ratio of masses becomes little m divided by little m, which is just +1. And so you can see that little v prime approaches the initial velocity when big M is much less than little m. So that's a picture that looks like this. Okay, so this guy's coming in like this, and this guy's a tiny fly there, and so nothing happens. So the final velocity of little m is equal to the initial velocity. Okay, and then we can look down to the other case, okay, where now we have a smaller mass hitting a larger mass at rest. Okay, and so now in this case, the final velocity of little m, which is this v prime, is negative, which means it bounces back. So if this is a very massive object, this is not very massive, and it's a perfectly elastic collision, then it goes doom doom. And v prime is negative, it bounces back. Okay, so this is bounce back. This is plows through. Does not bounce back. Okay, and then we can consider again the extreme case. So let's consider the extreme case where little m is much smaller than big M. So if little m is much smaller than big M, then in both the denominator and the numerator we can ignore little m compared to big M, and we get basically negative big M divided by positive big M is -1. Okay, so then v prime approaches negative v. So v prime approaches negative v when little m is much less than big M. And so the picture in that case looks like looks like this. Okay, then this tiny mass hits this big, nearly immovable mass, hardly moves, okay, and just bounces back like that. And so the final velocity is negative the initial velocity. Okay, so that's great. So that sort of deals with this term. It explains what this term is doing. Now let's look at this term, the 2m divided by the sum of the masses. And I'm going to erase this a little bit of the picture here, so we have a little bit more room. Okay, so now we're solving for the final velocity. Here we solved for the final velocity of little m. Okay, does it continue forward, or does it bounce back, or does it suddenly come to rest? Now we're going to solve for the final velocity of big M, which is big V. And let's put it here. So big V is equal to, big V prime is equal to this, and when the initial velocity of big M is 0, that term drops out, and we're left with twice little m divided by the sum of the two masses times little v. So first of all, you'll notice that there was a difference in sign here, so the final velocity of little m could have been positive or it could have been negative. Here, there's no sign change, no possible sign change. So big M always takes off to the right. Okay, so it always has some positive final velocity. Okay, so this is always positive. I suppose, or equal to 0 if little v was 0, or big M was huge compared to little m. Okay, so let's look at these cases. So there are 3 possible cases here. Okay, and let's look at the middle case first. In the case that little m is equal to big M, so it's like the billiard ball, it's like the cue ball hitting a colored ball in billiards. The masses are equal, and it's a head-on collision like this. Then what we know is that the cue ball, okay, the white ball, will come to rest, and we know that the colored ball will take off with exactly the same velocity. So we should have big V prime equal to little v, and let's see if that's right. If these masses are equal, then we have big M is equal to little m, the denominator is twice little m, the numerator is twice little m, and so big V prime, the final velocity of that colored ball, is equal to little v, the original velocity of the cue ball, or the white ball. Okay, so this makes sense. It makes sense because all of the momentum and kinetic energy of little m goes into big M. Okay? And so since their masses are equal, it has the same velocity. Okay, so that all makes sense. And then another case is for big M. So yeah, let's consider another case, which is big M is much bigger than little m. So if big M is much bigger than little m, we're talking about this being huge and this being small. So what we have is this kind of a situation where it's a small object coming in and hitting a large object like that. So then in that case, the final velocity, this is a huge mass here. So yeah, there's going to be momentum transferred from this guy to this guy and this guy back to that guy, but this guy is going to have very small velocity. Okay, so this guy's going to barely move, and so if big M is much bigger than little m, if we look at this equation, then big M is much bigger than little m, so we can ignore that, and we have basically little m divided by big M is a ratio of masses that approaches 0, as big M becomes huge compared to little m, and so this approaches 0. So the final velocity of big M approaches 0 as this guy gets really massive compared to that guy. Okay, so that makes sense. Okay, and then the final case, and this is the most interesting, the final case is when we reverse this, when we say, no, it's little m that's much bigger than big M. So now the situation looks like this. We have little m is huge, so we have a huge massive object moving like this, and it's going to hit a little tiny object that's at rest like that. Okay, and then in this case, something interesting happens. Okay, so now we have big M is tiny compared to little m. If big M is tiny compared to little m, we can ignore big M here, and we have in the numerator 2 little m, in the denominator we have just m. So this just becomes 2 times v. So this approaches 2 times v. I'll try to mix the 2 and the v together. So this is 2, it approaches 2 times v. And now we might wonder why. So this is a very interesting special case, which has a all kinds of super important applications like in the real world. So, so let's talk about that a little bit. So let me do that actually in this little space up here. I just need a little bit of space here. Okay, so I need a little bit more space here, erase it a little bit more, in order to deal with this really interesting final case. Okay, so in this case, the situation looks like this. We have a large mass which is moving to the right with a speed v, and it's going to have a collision with a very tiny mass that's initially at rest. Okay, so it's this very extreme case where big M is much smaller than little m. Now, what we're trying to understand is, why is it that after this collision, it's obvious why this large mass basically continues to move with the same velocity after the collision. It's not so obvious why this mass after the collision is, twice v. Okay, so why is that? Well, what we can do is we can look at this situation from a different point of view. Yeah, that's often useful in physics. Okay, so what we're going to do is we're going to take a different person's point of view. We're going to take the point of view of someone moving in an inertial reference frame that's moving with a speed v relative to the original reference frame. So in that moving reference frame, big M is at rest. So the guy that's standing on big M, what does he see? Well, he sees, oh, my mass is at rest. And so, and what he sees is, we see this guy moving toward that guy with a speed v, but this guy sees this thing moving towards him with a speed minus v, or speed v in the opposite direction. Okay, so this guy here, he sees that little object moving towards him with the speed v. And so this is a very large mass. So he's standing on this very large mass, and this little marble comes in like this, and there's an elastic collision. So whatever speed the marble had to begin with towards him will be the speed that the marble has after the collision. So this guy sees after the collision, he's still basically at rest, and this little marble has gone dung dung and is moving now to the right with the speed little v. Okay, so it's very easy to understand what's going on from the point of view of someone standing on the mass. But remember that the person standing on the mass, who's moving in that moving inertial reference frame compared to the original, is moving with a speed v relative to the original reference frame. And so to convert these two pictures, initial and final, to these two pictures, initial and final, we have to add a speed v to this entire picture and add a speed v to this entire picture. So when we do that, we add a speed v to this object, well, that becomes the very massive object moving to the right with a speed v. When we add a speed v to the right to this object, well, the negative v and the positive v cancel out, and we have a small object at rest. Okay, when we add, so that explains that one. When we add a speed little v to the right to this after picture, this final picture, we have a mass big M moving to the right. Okay, so it just sort of plows through. This has little effect on its motion, on its velocity. Okay, so this guy's moving to the right with speed v, but then this guy is moving to the right with speed v plus v, and that's where we get v plus v is 2v. That's where the 2v comes from in here, and that's what the factor of 2 represents in that equation. Okay, now this has a really interesting application. Okay, to, like I mentioned, to supernova explosions. Okay, so let's see how that works. So I'm going to give you sort of an example. This example, I think many of you might have even tried this example on your own. So the idea is, the idea looks like this. Suppose that you have two balls. One is a large basketball and one is a small, say, tennis ball. And then you put the tennis ball on top of the basketball, and then you drop both of them like this onto a hard surface, onto the ground. And what you notice happening is they go down like this, and then the basketball comes up, and so does the tennis ball. But the tennis ball comes flying up surprisingly quickly. Okay? And so why is that? Let's think about this a little bit. It has to do with this factor of 2 here. Okay, so we're going to assume we have a mass, we have a big mass, call this big M, and we're going to have a mass little m. And we're going to assume that big M is much bigger than little m. Okay, and what we're going to imagine is that this is the tennis ball and this is the basketball, and we've held them together and then released them. And just to make it easier for us to understand, we're going to imagine that we put a small gap between the tennis ball and the basketball before we release them. Okay, so then the tennis ball and the basketball will fall together with exactly the same acceleration, and then so just before they hit the ground, they will have accumulated some downwards speed. So big M will be moving downwards with some speed. What are we calling this? Little v, like this. Okay, and then what we do is, and they're right next to the ground, a hard ground like this. And then what's going to happen is, first, the basketball, the big M guy, is going to hit the ground, and we're going to assume that these are elastic, perfectly elastic balls, like super balls. Okay, so none of the kinetic energy is converted into thermal or other forms of energy. So then this guy, this basketball, hits the ground, compresses like a spring, and then bounces up off the ground. And so that basketball is going to hit the ground and bounce up, and it's going to bounce up with exactly the same speed that it had on the way down. But this guy, we're going to assume it goes, like this, bounce, bounce, but we're catching it just before little m has hit, before the tennis ball has hit the basketball. So the tennis ball is still coming down with a speed v like this. Okay. Now here comes the crucial part. So the crucial part is what happens when we have the basketball that's moving up with a speed v hit the tennis ball that's moving down with a speed v down. Okay, what's going to happen? Well, let's see. So first of all, this is a very small mass object compared to this object, and so it doesn't matter what velocity this object had. Basically, this huge massive object is just going to plow through. And after the collision of the tennis ball with the basketball, the basketball will still be moving with at least roughly a speed v upwards. So this is now after they have collided. Okay, and so this guy is still moving up with at least approximately the same speed v. But now this tennis ball, what's it doing? Well, let's suppose that the tennis ball was initially at rest. Okay, so suppose it was at rest when the basketball hit it. Well, we know the answer. Okay, if a large ball hits a small ball, the large ball is moving with speed v, and it hits a very small ball, then that was initially at rest, and then that small ball that's initially at rest will have, after the collision, a speed 2v. Okay, so if the tennis ball were initially at rest when the basketball hit it, this guy would be flying upwards with a speed that's equal to 2v. Okay, at least approximately. Okay. That's the effect that we just talked about. But now, this tennis ball was not originally at rest with a big ball of speed v hitting it. Okay, it was actually moving downwards. Okay, and so that even if this guy was at rest, this tennis ball would be coming down with a speed v, it would bounce off the basketball and return with a velocity little v upwards. Okay, and so we have to add, because of this initial downwards velocity, we have to add an additional velocity little v to this. And so the total velocity upwards of the little ball is actually 3 times v. Okay, now this is getting interesting. So let's now take this effect and let's amplify it by stacking more balls on top of each other. Okay, so so we start with, let's try 4 balls. Okay, so then the effect becomes really dramatic. Okay, so we have this really big ball, and stacked on top of this is a smaller ball. Stacked on top of this is a smaller ball. Stacked on top of this is even a smaller ball. And now what we're assuming is that the mass of this ball is tiny compared to the mass of this one. The mass of this one is tiny compared to the mass of this one. The mass of this one is tiny compared to the mass of this one. And we're also assuming that no kinetic energy is converted into other forms of energy like thermal and so on and so forth. Okay, so obviously this is an approximation, but at least we can get a feel for this amplification of velocities here. It's super cool. It still conserves momentum and energy, of course, but there's this weird amplification of velocities. So we have these 4 balls stacked on top of each other, and we drop them all together. Okay, and so obviously they accelerate with exactly the same acceleration. And so just before they hit the ground, they're, say, all of them are moving with the same velocity v down. Okay, so this is v. V, 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 V. Okay? And then what we do is we think, okay, well, as soon as this largest ball hits the ground and bounces up, Okay, we've put a little gap here to aid our thinking here. So the big ball hits the ground and bounces up. Well, when it bounces up, after the bounce, it's going to be moving with a speed v that's upwards. These are like perfectly elastic balls. Doom, doom, right? Okay, but now this ball of this large mass of velocity v up is going to collide with a smaller mass of velocity little v downwards. Okay, that's exactly this situation, up v, down v. And so we have this situation that there's this factor of 2 that happens, even if this guy were at rest. Then when this big mass hits this small mass, this smaller mass will take off with an upward speed of 2v. Okay, so there's a 2 times the original v, this speed here, okay, the speed of the lower ball, the more massive lower ball, and then you add to that the effect that, so this is the speed it would have 2v if this ball were at rest, but this ball is not at rest, it's coming down with a speed v. So even if this one is at rest, it would go doom doom and come up with a speed v. So you add an additional v due to this original downward velocity of this second mass here. Okay, and so then what you get is 2v plus v is 3v. Okay, so that's that case. And now we amplify this. And so this, if this is little v, then this is 3v. Okay, 1, 2, 3v. And then we come to this example here, and we play exactly the same game. We have, say, a massive ball hitting a very much less massive ball like this, and the same effect will happen. What will happen is you take twice, if this factor of 2 here, this factor of 2 here, you take twice the velocity of the ball below it, which was 3v, and you add to it the fact that this ball was not at rest when this ball hit it. It was actually moving down. So even if that one was at rest, this one would go dunk dunk and be moving upwards with the speed v. So you add another v. So this is 2 times 3 is 6, plus 1 is 7v. Okay? And then we come to the final one over here. So 7v is like really big. So 7v is, well, 7v is like this. Okay? 1, 2, 3, 4, 5, 6, 7. And then in this final case over here, what we have is, again, this factor of 2, which comes from that, times the velocity of the ball below it on its way up, which is this 7v. Okay, and then we add the velocity that the top ball had in the downwards direction. So plus v. So now we have 2 times 7 is 14, plus 1 is 15v. Okay, so if you have a stack of 4 balls like this, of all sort of descending masses like this, and it's a pretty elastic situation, then when you drop them like this, that top ball will take off with enormous velocity. Okay, it's like super much larger than you would expect. So like 15v is like this, okay, compared to the original. Now, why is this interesting in the real world? Well, it's interesting in the real world because supernova explosions are like this. Okay, so you have a core, and you have shells. You have shells of mass, like this. Okay, and these shells of mass are, they're more dense closer to the core, and then less and less dense. It's kind of like large mass, smaller mass, smaller mass, smaller mass. Okay, and then when there's a core collapse, what happens is, so this is the core, and then when it collapses like this, it basically free falls down like this. And so all of these shells of mass, they free fall down, just like these guys free falling like this. Okay, and then they all compress. They all compress to, well, basically sort of nuclear densities, and then they rebound. Okay, and so it's like hitting a hard ground like this. So you have all these falling layers of decreasing mass as you go further out, free falling like this. Then they sort of hit the ground, so to speak, and then they all bounce back. And then this inner layer, bounces back with some velocity, but the next layer up bounces back with a higher velocity, and so on. And then the outer, least massive shell, just blasts out with an enormous velocity. But in the entire process, of course, energy and momentum are conserved. But it's very, very cool. So there's all kinds of interesting examples like this. So this is called, it's called the Astro Blaster. And you can get this little toy that does this. And usually, if it's not COVID times, I would do this demo. It's really surprising. And but anyways, you can watch those YouTube videos of this Astroblaster. It was invented by a guy called Sterling Colgate. He was an astrophysicist who sort of thought of this kind of analogy of a supernova explosion. So anyways, so that's it. That's the Astroblaster. And this is a good example of collisions in one dimension, elastic collisions in one dimension.